So good morning, everyone, and welcome to today's lecture. This is lecture number 2 of photoelectric effect, and we'll try to wind it up in today's class. Just a recap of what we had done in the previous one. We had seen the dual nature of light, and we had seen that according to Einstein's photon theory or Planck's theory, we understand that light consists of small packets. The smallest packet of light is known as a photon. It does not have a rest mass. It only exists when it is moving. The energy of a photon is given by hf. Hc by lambda. H into C is 12,400 electron volts divided by Armstrong unit. Lambda in Armstrong unit. We'd also seen that particles which are moving may have wave as well as particle nature. If the particles are big, their wave nature is the wavelength is very small, therefore we sometimes neglect it. But if the particle is small, which has a momentum such as a moving electron or a moving proton, it can be associated with a wavelength. That wavelength is known as the de Broglie wavelength, and we had seen how do you find out the wavelength of de Broglie wavelength. These waves are known as matter waves. Do we remember this?
Yes, sir.
Now, there is a high probability that you might get a question based on this photons and matter waves, and this is the question that I am going to do. It's a question that has come in one of the previous years, and I hope that you can get a similar question in this year's. The energy of a photon is equal to kinetic energy of a proton. One is a photon, the other one is a proton. The energy of the photon is E. Let lambda 1 be the de Broglie wavelength of the proton, and lambda 2 is the de Broglie, no, not the de Broglie. Lambda 2 is the wavelength of the photon. What is the ratio of lambda 1 to lambda 2? I'll give you 2 minutes to give me the answer. Option B, I think, is the correct answer. Lambda 1 is the wavelength of the
ME
proton, that will be equal to
H by under root 2 ME.
h by under root 2 me, where E is the kinetic energy of the proton.
Yes,
I hope I have not used photon. Lambda 2 is the wavelength of the photon. Photon is hc by E. Yes or no?
yes, sir.
From here, you can straight away find out lambda 2 by lambda 1. If you find out the ratio, lambda 2 by lambda 1.
Sir, lambda 1 by 2.
Oh, sorry. Lambda 1 by lambda 2, you will get lambda 1 by lambda 2 will be proportional to rest all of them are constants. So you will find that it is going to be coming proportional to root over e by 2, and that is the answer that we are looking at. Do we understand this?
Yes, sir.
This, my dear friends, is the next question. The kinetic energy of an electron and a proton is given, which is same. What is the relation between their de Broglie wavelength? I'll give you a minute to give me the answer. Option A, I think, is correct. For any charge body, the de Broglie wavelength is given by h divided by under root of 2m into E. Now everything is same. H is a constant, mass, energy of both the bodies are same. So you can see lambda is proportional to 1 by root over m. The body which has more mass will have less lambda. Who has more mass? Obviously, the proton has more mass. Therefore, the wavelength of proton will be less than the wavelength of the electron. We are talking about the de Broglie wavelength. Do we understand this?
Yes, sir.
These are the questions that are more likely to come, and you can find one of these in one of the sessions that you appear. This is the next one. The energy of a proton and an alpha particle are same. What would be the ratio of wavelength of proton and the alpha particle? Again, this question comes from the same concept. Lambda is proportional to 1 by root over m with same energies, charged particles moving with the same energy. So I can write lambda of proton divided by lambda of alpha particle will be equal to root over mass of alpha divided by the mass of proton. And I told you many times that mass of the alpha particle is how much?
4, sir.
Is 4 times the mass of the proton, and that gives you the revolutionary result 2 is to 1. 2 is to 1 is the answer for this gentleman. Do we understand this?
Yes, sir.
There comes the next one in this category, and the next one in this category is this one. The de Broglie wavelength of a particle accelerated with 150 volt is 10 raised to the power minus 10 meter. If it is accelerated by 600 volt, what will be the wavelength? Well, from where does this fact come? V is proportional to lambda is proportional to 1 by root over V. You may not remember what was there in the numerator because that does not matter. It was 12.27 or 0.238. Doesn't matter. What you must remember is lambda is inversely proportional to root over E. Therefore, it is also inversely proportional to root over V. If you remember this fact, lambda 2 in the second case divided by lambda in the first case will be under root of V1 by V2. The ratio of V1 by V2 is 1 by 4. Yes or no?
Yes, sir.
1 by 4 root is half. So the wavelength will become half. Wavelength becoming half of 10 raised to the power minus 10. 10 raised to the power minus 10 is 1 Armstrong. Wavelength becoming half. The answer would be 0.5 Armstrong units. Do we understand this?
Yes, sir.
Everyone understands this?
Yes, sir.
Okay, the more the number of questions you do, the better you are, and more is the probability of the same question coming in the examination hall. This is the question. It might look somewhat different, but this is there just to prove a point. I'll give you 2 minutes to give me the answer. What is the de Broglie wavelength of an electron which is moving in an orbit of circumference 2 pi r? So how are we supposed to solve this? Well, the de Broglie wavelength of any electron will be given by h by p, yes or no?
Yes, sir.
Which is nothing but equal to h by mv. Do we understand this?
Yes, sir.
Just have to find out the value of h by mv. Mv is the momentum of the proton, of the electron. How do you find the momentum of this electron? MVR is nh by 2 pi. Yes or no?
Yes, sir.
So from there you can find out the value of h by mv. H by mv will be equal to what? 2 pi r divided by n. Yes or no?
Yes, sir.
So this is equal to 2 pi r divided by n. Yes or no?
Yes, sir.
And this becomes a very important relation for an electron moving in a circular orbit. The wavelength lambda, the de Broglie wavelength, will be given by 2 pi r divided by n. A very, very important result. If we put the value of n as 1, the answer would be matching with 2 pi r. If the value of n was given as 2, which is not mentioned in the question, the answer would have been pi r. So this gives us a very important result, that the de Broglie wavelength of electron in the first Bohr orbit, this was the first Bohr orbit, it will be equal to the circumference of the orbit. You just have to find out the value of mv, and that will end up with your result. Do we understand this?
Yes, sir.
So if this question would have been given in such a way that an electron is moving in the fourth orbit, the radius of the orbit is r. What is the de Broglie wavelength? The answer would have been 2 pi r by 4. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Here you can note one more thing. Apart from de Broglie wavelength of an electron moving in a circular orbit, they might sometimes ask you, very rare cases, maybe in JEE Advanced, the de Broglie wavelength with gas molecules. The de Broglie wavelength of gas molecules is defined by this formula, and I hope you understand what is VRMS here. What is VRMS here?
RMS speed of gas molecule.
RMS speed of gas molecule. So it can be written as h by root over 3 mkt. You can understand that you can write VRMS speed as root over 3 kt by m. Yes or no?
Yes, sir.
From there comes this formula. I hope you understand how this formula has come. Yes or no? No or yes?
Yes, sir.
So it will be inversely proportional to the mass of the gas molecule under root, and again it will be inversely proportional to root over temperature. Keep this. If a question comes, well, this is +4 for you rather than -5. Then we have this question, and I hope you can answer this. The de Broglie wavelength associated with an hydrogen atom moving with a thermal velocity of 3 km per second. When they say thermal velocity, which velocity are they referring to?
VRMS.
They are referring to the VRMS. So I'll give you 2 minutes to give me the answer. So how are we supposed to do this? The wavelength will be given by h by m VRMS. The value of h is not given. It is 6.6. Forget about the multiples because all the answers are given in the same unit. So you must not worry about the powers. VRMS, mass of the hydrogen atom. How much is the mass of the hydrogen atom? 2 into 1.67 into 10 raised to the power minus 27 kgs multiplied by VRMS is 3 into 10 raised to the power 3 meter per second. Multiply, divide, and I think now you have to look at the powers as well because the answer are given as 0.66, 6.6 and 66. The answer that I have is 0.66, so that should be the right answer, and that is how you have to do a question of this nature. I hope you understand this. Everyone understands this? In this mass of hydrogen atom, I've assumed, not assumed, that there is one proton and one neutron. Is there a neutron there?
Sir, hydrogen has only one proton, sir.
Right. So the answer has to be not 0.66. It has to be the 2 must go away. So the answer would be whatever you get from here. Okay. In this sheet of mine, there is a mistake. So whatever you get from here would be your answer. Okay. The answer that I have is 0.66. I don't know whether you are going to get 0.66 from here. 3 into 1.67. Yeah, 3 into 1.67 will not give you 6.6. So there must be a mistake in typing somewhere. Okay. So you understand how are you supposed to do this?
Yes, sir.
Okay. Anyways, you can try this one and I hope this answer is correct. The de Broglie wavelength of a neutron at 27 degrees Celsius is lambda. What will be the wavelength at 927 degrees Celsius? You must remember this lambda for a neutron is inversely proportional to under root T, where T must be the temperature on Kelvin scale and not the degree Celsius scale. Do you understand this?
Yes, sir.
So from there you can see lambda 2 by lambda 1 will be under root of T2 by T1. T2 is 1000.
Sir, T1 by
No,
T2.
sorry, T1 by T2. I always make mistakes in ratios. T1 by T2. I think T1 is 12. T2 is 1200 and T1 is 300. Yes or no?
Yes, sir.
So it becomes 1 by 4. Root of 1 by 4 is half. So the wavelength has to become half, and that is the answer that we are looking at. Everyone understands this?
Yes, sir.
This is the next one. This is just to explain something. A steel ball of mass 1 kg is moving with a speed of 1 meter per second. What is the de Broglie wavelength? The de Broglie wavelength is simply given by lambda is equal to h by mv. Mass is 1 kg. Velocity is 1 meter per second. So this lambda will come equal to h, and the value of this h is 6.6 into 10 raised to the power of minus 34. And as you can see, this wavelength is very, very small. You cannot observe it. And therefore, we will say a steel ball moving, though it has a de Broglie wavelength, the wavelength is very small. So we cannot treat it practically as a wave. We have to treat it practically as a particle. Do we understand this? Therefore, this is a particle and this is not a wave. We understand this?
Yes, sir.
Then this is the next category of question that can come. The question that asks you the percentage error or percentage change or this or that. When the momentum of a proton is changed by an amount P naught, the corresponding change in the de Broglie wavelength is found to be 0.25%. What is the original momentum of the proton? So, how do we get this? Well, you know that lambda is inversely proportional to the momentum. Yes or no?
Yes, sir.
Now, lambda is inversely proportional to momentum. Just try to explain it to you. Or you can write lambda into p is a constant. Yes or no?
Yes, sir.
If you differentiate both sides, you will get d lambda into p plus dp into lambda is equal to 0, or simply you will get dp by p. You can write it as the error wala equation minus d lambda by lambda. Do we understand this?
Yes, sir.
That's it. dp by P is minus of d lambda by lambda. What it suggests is when wavelength is decreased, momentum increases. Do we understand this? If I talk about only the magnitudes of this, you can write the change in momentum divided by P will be equal to magnitude wise change in lambda divided by lambda. Yes or no?
Yes, sir.
The change in momentum in this case is given as P naught divided by the original momentum P will be equal to d lambda by lambda. D lambda by lambda is given in terms of percentage 0.25. So it will be 0.25%. So it is percent, so it is divided by 100. Yes or no?
Yes, sir.
From here, you should be getting the value of P as 400 P naught, and that is the answer that we are looking at. Do we understand this?
Yes, sir.
Here comes the next question. The de Broglie wavelength of a vehicle is lambda. The load is changed so that the velocity and energy both are doubled. What is the new wavelength? How do we get this? The lambda is given by h by mv. Yes or no?
Yes, sir.
The energy of this vehicle, when we talk about this energy of the vehicle, we are talking about the kinetic energy of this vehicle. Yes or no?
Yes, sir.
Now remember, the mass is constant here. What is changing is the velocities and the energies. You can eliminate mass in between the equations. Yes or no?
Sir, load is changed.
The load is changed so that the velocity. Oh yes, load is changed. That means the mass has changed, and in such a way that velocity and energy both are doubled. What will be the new wavelength? So basically,
M is directly proportional to E by V square.
yes, we have to look at how much the mass would have changed and how much the velocity would have changed. So from the first equation, I can write this lambda is inversely proportional to 1 by mv. The velocity has been doubled. How it has been doubled? The load has been changed. That means the mass has been changed. So you have to find out what is the change in mass. Here you can write mass as 2e by v square. Energy has been doubled. So this mass is proportional to E by V square. Yes or no?
Yes.
Now I can write this here. So lambda will be proportional to 1 by E by V square multiplied by V. So lambda will come proportional to V by E. Yes or no?
Yes, sir.
Now the ratio of V by E remains same, and therefore the answer is simply equal to lambda. Do we understand this?
Yes, sir.
Be very careful about such questions because you might just write the wrong answer. You might just, which I was trying to do, but you did not let me to do it. You might just write the answer from here. The velocity is doubled, so lambda will become lambda by 2. No, the mass has also changed. So you should not jump on to conclusions looking at one equation. Do we understand this?
Yes, sir.
That is the reason that lambda by 2 was also given as one of the options. Anyways, this is a question that has come in one of the previous year IITs. Very likely it can come in your IIT as well. A particle of mass m, when it comes in an IIT, it will probably come in a JEE Advanced. The particle of mass m decays at rest into two particles of mass m1 and m2 having non-zero velocities. The ratio of de Broglie wavelength would be how much? Option C, 1. How did you get option C?
Sir, I have taken M1 V1 plus M2 V2 equals to 0.
If this is your mass, this capital M mass was at rest, it decays into 2. Now, if one of the masses, let us say M1, moves with a velocity V1 in this direction, how will the other mass M2 move?
Moves in the opposite direction.
It will have to move in the opposite direction with a velocity v2. The velocities will not be equal in magnitude, but they will be opposite because the total momentum has to be 0. Do we understand this?
Yes, sir.
So the momentum of these particles, m1 v1, in magnitude must be equal to m2 v2, and in direction it is going to be opposite. Yes or no?
Yes, sir.
And we already know that what? Lambda is proportional to 1 by p. Yes or no?
Yes, sir.
It has got nothing to do with lambda is a scalar quantity. It has got nothing to do with direction. It has got only to do with the magnitude of momentum. The magnitude of momentum is going to be same, my dear friends, and therefore the answer is going to be 1:1, same. Do we understand this?
Yes, sir.
This is the next one. A curve drawn between velocity and frequency of a photon in vacuum will be. What is the answer for this one?
Sir, option D.
The curve drawn between velocity and frequency of photon. What is a photon? What is a photon?
Mm, Particle which carries energy.
What is a photon? Go back. Tell me what is the definition of a photon. That is how we started last class. We dedicated the last class on
Sir,
photon.
it is energy packet.
The smallest packet of light. Light has got dual nature. Electromagnetic radiations have got dual nature. The smallest packet of light is photon. What is the speed of photon in vacuum? You don't know it?
Sir, it is
Yes?
P. That is speed of light.
Well done. We know this, that the speed of photon in vacuum is the speed of light. Can you change it? In vacuum, can you change the speed of light?
No, sir.
Congratulations. We now realize that we cannot change the speed of light in vacuum. Now we read the question again and get the answer. The curve drawn between velocity and frequency of photon in vacuum will be.
Option A, straight line parallel to frequency axis.
See, God exists. I always start believing that God does not exist. But then I get fabulous answers that makes me realize that God exists. And God has made speed of light constant in vacuum, my dear friends. And therefore it is a straight line. We all believe now that God exists. God exists, yes or no? God exists, yes or no?
Question mark.
The speed of the light in vacuum remains constant, yes or no?
Yes, sir.
Thank God. That takes us to the next heading, which is known as electron emission. What is this electron emission? What is this electron emission? What is this electron emission? Yes, my dear friends, what is this electron emission?
Loss of an electron from an atom or molecule.
Well, inside an atom, there are free electrons. Free. They are free to move. Can they leave the metal surface and become actually free from the metal? This is the metal, iron, and all of a sudden electrons start jumping out from there. Can that happen? Do you understand the question, what I'm saying?
Yes, sir.
They are free electrons. Can they escape the metal just like that? I have an iron rod, and all of a sudden electrons start jumping because they are free. Does that happen?
We should provide some energy.
They cannot escape the surface of the metal. They are free, but they are only free inside the metal. Inside the metal, they are free to do anything. Like inside your class, no one is seeing, and you can do anything. If you want to, if you want to make these electrons free, what you got to do?
We have to
What
give energy.
you have to?
Provide some energy.
You have to provide some energy. And once you give this energy, what happens? They have to overcome something known as a barrier. You can call it as, we are going to call it as work function actually. We are going to call it as work function. So they are not free to leave the metal surface. They can only what? Move inside that metal. Now, in order to make them free, we need to provide them energy. You don't have to write all this. This is just to explain. That electrons are free only inside the metal. They just cannot leave the metal surface. If you give them sufficient energy, they might leave this metal surface and become free. This phenomena is known as the phenomena of electron emission. So when electrons are given sufficient energy, they can leave the metal surface and become free. This phenomena would be known as what? This phenomena would be known as the phenomena of electron emission. So electron emission is the phenomena by which electron get sufficient energy and they are free from the surface of the metal. Do we understand this?
Yes, sir.
Now, if we have to give them energy, we'll have to give them energy in some way. We'll have to give them energy in some way. What are the ways in which you can give these electrons energy? Can you think about some ways in which you can give them energy? What are those ways in which you can impart these electrons energy?
By striking a light.
By striking light, because this is the heading of this chapter, therefore you have thought about this. Okay, before going into this, let us let us understand the term work function. Work function. So we can write the term work function, or sometimes it is known as threshold energy. Work function or threshold energy, it is written as W or phi, doesn't matter. What is this work function or threshold energy?
The minimum energy required for electron to leave the metal surface.
Yes, the minimum energy required to emit electrons from any surface. It could be a metal, it could be anything. You must give it some minimum amount of energy so that electrons can be emitted. That would be known as the threshold energy or work function. Now, how are you going to give the electrons this energy? The first way and the easiest way that I can think of is to heat them up. If I heat the metal surface sufficiently, by heating, I raise the temperature, and by raising the temperature, I increase the speed of the electrons. They get enough energy. If they get enough energy, they will be able to leave this surface. This type of emission is known as thermionic emission. So thermionic emission is the emission of electrons from a metal surface by heating it up sufficiently. Do we understand this?
Yes, sir.
This is the first type of electron emission, which is known as thermionic emission. You just write the heading thermionic emission, and then you can write thermionic emission is the process in which electrons are given sufficient energy so that they can escape the metal surface. Do we understand this?
Yes, sir.
Now, what could be the next type of electron emission? What is the other way in which you can give these electrons energy so that they can leave the metal surface? The second type of emission may be known as or is known as the field emission. What do you mean by field emission? If you place this metal in an electric field, this electric field is going to accelerate these electrons, yes or no?
Yes.
The energy they will acquire will be given by Q into V, yes or no? We have just seen that so many times, yes or no?
Yes, sir.
If I put sufficient electric field, I may be able to eject electrons. Remember that dielectric breakdown of insulators. Remember that? If I put electric field strong enough, even insulators can start, the electrons become free from that atom and they become free to move inside that insulator. Remember that?
Yes.
Here what is going to happen is I'm going to put the metal surface in an electric field, and if I make the electric field strong enough, the electrons can get sufficient energy, they can leave the metal surface and become free. This type of emission, my dear friend, is known as, it's known as what?
Field emission.
Field emission. That is the third form of electron emission, which is known as, that is the second type of electron emission, that is known as the field emission. So I can emit electrons in this fashion. What can be the third way of, have you written this? You just need to write field emission and just write, if sufficient electric field is applied, electrons can become free. Have you noted it down?
1 minute.
Okay, let me know once you are done. What is the next type of emission is known as secondary electron emission. What is this secondary electron emission? If a beam of high velocity electrons, I have an electron beam and I strike this electron beam on any metal surface. Now when this electron beam strikes on any metal surface, these electrons in this beam have high kinetic energy. If they collide with the revolving electrons, they will be able to emit these electrons from the metal surface. Well, my dear friends, that type of emission of an electron by the use of high energy electron beams is known as secondary. Why it is known as secondary? Because primary electrons are already there, which is moving and striking the electrons on the metal surface. This type of emission of electrons by striking it with another electron beam is known as secondary emission. I'll give you a minute to just note it down in very short. What could be the next way in which you can emit electrons from a metal surface? Light has got energy. Light has got photons. These photons has got energy. These are just, you can treat them just like particles because this is particle theory of light. Light has got a large number of particles, photons. Duk, 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 duk. When these photons strike the metal surface, they can impart their high energy to this metal surface. These electrons can absorb that energy, and that energy is sufficient enough. Electrons can be emitted from the metal surface. This phenomena is known as the phenomena of photoelectric emission. Do we understand this?
Yes, sir.
So what is photoelectric emission? What is photoelectric emission? What is photoelectric emission? Yes, my dear friends. Photoelectric emission or photoelectric effect is the phenomena of emission of electrons from the surface of metals when light of suitable frequency falls on them. The emitted electrons are known as,
Photoelectrons.
and the current is known as,
Photoelectric current.
and this phenomena is known as photoelectric effect, and this is based on, everything is based on the law of conservation of energy. These photons have energy, they impart this energy, some energy is lost in form of heat, some energy is lost in that form. If it has sufficient energy, electrons will be emitted. Welcome, my dear friends, to photoelectric effect. Then let's us move ahead. Who observed this photoelectric effect? Any idea? Who observed this photoelectric effect for the first time?
Einstein, sir.
Not Einstein. See. Not necessarily that what we know is correct. Einstein did a lot of pioneering work on this, but the gentleman who observed this what hurts in the year of 1887. He observed this effect. What did he observe? That can anyone explain what is happening here? What did Hurt observe?
Sir, it is cathode ray experiment.
I don't know what is cathode ray experiment. This is okay. Tell me what is cathode ray experiment. I don't know what is cathode ray experiment. Tell me what is. Since you see a cathode ray experiment. Every terminal of a cell or something will have a cathode and anode. That does not become it. That does not mean that it becomes a cathode ray or anode ray experiment. What did Hers observe? It's written in English. It's drawn in a diagram. You just have to read it and tell me. What did he observe? He had a evacuated quartz tube. Sometimes we call it a discharge tube. What do you mean by evacuated? You evacuate the building. What do you mean by that? We leave the building. The building is empty. Evacuated quartz tube is a tube from which air has been sucked out. What? So the vacuum tube. And this ding 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 ding. What is this ding 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 ding? This ding 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 ding. Do you see this ding 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 ding? What is this? These are ultraviolet rays having sufficient energy. And when they strike this surface, what happens? Electrons are emitted, and they start moving towards the anode, and a current is established in the circuit. So from here, you observe this phenomena, which is known as the phenomena of photoelectric effect. When light of sufficient frequency, or energy falls on a metal surface, this happens. Do you understand this, or this is going above our head saying bye bye?
Understood.
That is what was observed by Hertz. Now, a term that always comes in this is work function. So we'll again have a look at this work function or threshold energy. What is work function or threshold energy? It is the minimum energy which is required to make an electron free from the metal. Threshold frequency, work function phi or W is the minimum energy required, and therefore you must be having light of sufficient energy. Yes or no? If the light is not of sufficient energy, then you will not observe any photoelectric effect. Do we understand this?
Yes.
So I can write this W or W naught or work function as the minimum energy required. Now that minimum energy required can be written as H into F naught, and that can be written as H into C by lambda naught. Where what is this F naught and lambda naught? This can be written as 12,400 divided by lambda naught in Armstrong unit. What is this F naught and this lambda naught? This F naught is known as threshold frequency, and this lambda naught is known as threshold wavelength. What is this threshold frequency and threshold wavelength? We'll note this down and we'll come back to it. So what is this threshold frequency or what is this threshold wavelength? Can anyone tell me? What is this threshold frequency or threshold wavelength? To emit electrons from a metal surface, we need radiations of certain minimum energy. The certain minimum energy which is required to emit electrons is the work function. If your energy of the radiation is less than the work function, no electron emission will take place. Now this energy of the radiation depends on the frequency of radiation. E is equal to hf. Therefore, we need a minimum frequency for which electrons can be emitted. That minimum frequency it is required to emit electrons from a metal surface is known as the threshold frequency. If the frequency of the striking photons is less than the threshold frequency, no photoelectric current would be observed and there will be no photoelectric effect. What is the relation between F naught and W naught? W naught is the work function. W naught will be equal to H into F naught. Do we understand this?
Yes.
Now, since we have related it to frequency, we'll also relate it with the wavelength. The maximum wavelength for which electrons can be emitted. Remember, frequency was minimum, therefore wavelength is maximum. The maximum wavelength of the incident photons for which electrons can be emitted is known as the threshold wavelength. This W naught will be equal to Hc by lambda naught. Do we understand this? Yes or no?
Yes, sir.
I'll give you 2 minutes to note this down. Then we come to the next heading, the most important heading of this chapter. And we'll do a lot of work on this because the numericals are going to come from this part only, which is known as the Einstein's photoelectric equation. Do you know that Einstein got a Nobel Prize in physics? Do you know this? Sir Albert Einstein got a Nobel Prize in physics. Do you know this?
Yes, sir.
For which work did he get the Nobel Prize in physics? And it's a good day to discuss this because today, if you might know, is celebrated as National Science Day. Do you know this? Yes, some of you know it. Why it is celebrated as National Science Day? So today is holiday, that's it. Why we have to remember?
Sir, today is like every day for us.
Today is like every day for us. As students, you must remember some things in life. And as science student, you also must remember some very important things in life. Today is National Science Day. Why it is celebrated?
Don't know, sir.
We are chilling out. Have you heard the name of Sir C.V. Raman?
Yes, sir.
The only Indian, born Indian, lived in Indian, lived Indian, born Indian, taught in Indian, died in India person who got the Nobel Prize for Physics. Heard that some Indian got a Nobel Prize for Physics? Not Indian born Australian or American citizen, Indian born Indian, lived and died in India citizen. Sir C.V. Raman, knighted by His Majesty the King, or Her Majesty the Queen, knighted for his achievements, something known as the Raman effect. He got the Nobel for that. Today is his birth anniversary. Anyways, Sir Albert Einstein also got a Nobel Prize. Do you know for what? Which work he got a Nobel Prize? What do I do? I'm no Einstein, sir. I'm not going to get the Nobel Prize. So why? Let's move on. He got the Nobel Prize for is what we are going to study now. Einstein's photoelectric equation. He got the Nobel for this prize. He got the Nobel for this achievement, not for E is equal to mc square or general theory of relativity. Did not get any Nobel for that. He got the Nobel for this one. Sir Albert Einstein's photoelectric equation. Raman effect, we are not going to study in 12th syllabus. Maybe your children might study it, not us. We are going to study Einstein's photoelectric equations. What happens when a photon falls on a metal surface? You can see the jig 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 jig. What is jig 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 jig? This jig 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 jig. This jig 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 is the incident photons or radiations which are falling on this metal surface. Now this energy of this incident jig 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 is E is equal to HF. This much energy this jig 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 has. Now when this jig 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 falls on a metal surface, what is going to help? There may be some electrons which are lying on the surface. There may be some electrons which are under the inside the metal. So some energy would be used in shifting the electron which is inside the metal onto the surface of the metal. Yes or no?
Yes.
Some energy would be lost in collision of this electron. So we call that total energy as W in shifting the electron from inner to the outer surface and in collisions. When these electrons get energy and it try to come out of the metal surface, they might collide with the corresponding with the neighboring electrons and some amount of energy is transferred there. Do we understand this? Let me call that energy as W. Then we need an amount of energy W naught to free this electron from the metal surface. Do we understand this?
Yes.
And the rest of the energy, will be emitted as the kinetic energy K. I forgot to mention that will be emitted as the kinetic energy K of the electrons. Do we understand this?
Yes, sir.
And remember, this Einstein's photoelectric equation is based on which principle?
Conservation of energy.
Everything is conservation of energy. Based on the law of conservation of energy. So what will be the energy equation for this one? E, which is equal to HF, will be equal to what?
Hf naught plus kinetic energy of the electron.
W plus W naught plus the kinetic energy of the electrons which are emitted. Do we understand this?
Yes, sir.
If we take W as 0, when you say W as 0, that means no energy is transferred or lost in moving the electrons from inside to the surface. The electron does not collide with any of the neighboring particles. It absorbs the entire energy and it just goes out. In that case, the kinetic energy of the electron will be maximum. Yes or no?
Yes, sir.
In that case, the equation becomes E is equal to W naught plus KE max. Because the entire energy is utilized in overcoming the work function and the rest of the energy is given to the electron. And my dear friend, this equation is known as
Photoelectric equation.
This equation is known as Einstein's photoelectric equation. And my dear friends, this is the revolutionary equation for which Sir Albert Einstein got his share of Nobel Prize. Einstein's photoelectric equation. E is equal to W naught plus KE max. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Then comes the next most important aspect of this chapter is to understand what happens and how do we observe this photoelectric effect. So again, you have this tube. You can call this evacuated quartz tube or vacuum tube or whatever. It has been evacuated. There is no air inside. Then you have a voltmeter here to measure the potential difference between the anode and the cathode. Anode is negatively charged, anode is positively charged, and cathode is negatively charged. Yes or no? Then you have this emitter, which is just to measure the current which is flowing in the circuit. Now, when you allow light of sufficient frequency, jhag 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 jhag, to fall on the plate P, this plate P is a photosensitive material. It has got a very small work function. So when light of sufficient frequency or radiation of sufficient frequency fall on this plate P, electrons can be emitted. Yes or no?
Yes, sir.
Now, when P and Q are kept at the same potential, we can change this potential by taking a rheostat. I don't want you to get into complicated diagrams. You can change the potential difference between this P and Q by adjusting the battery. You can adjust the battery by changing the resistance of the circuit and all those things. When P and Q are at the same potential, a very small current flows, which is of practical zero importance. Now remember, whenever this photoelectric emission is observed, we have seen the Einstein equation and we have seen this maximum kinetic energy. Now this maximum kinetic energy is not for all the electrons, because all the electrons are not going to absorb the entire energy and move out. Only very few electrons will absorb that energy and move out, because most of the electrons will be colliding with the other electrons and losing a part of that energy. Do we understand this?
Yes, sir.
So when you keep anode and cathode at the same potential, only those electrons will be emitted which will have still energy left to come out of the metal and go from P to Q. It's a very small current which has got practically no value, so there is no point of discussing that current. This current comes because of the kinetic energy of electrons. This kinetic energy of the electrons is only coming from the fact that energy is falling on them. They are absorbing it. Some energy might be lost. Whatever energy is left, they are able to come out. Do we understand this?
Yes, sir.
But now, if I make the plate Q positive with respect to the plate P, I make the plate Q positive with respect to the plate P, the current will increase because now more electrons which may not have sufficient energy, they have come out of the metal, but they do not have sufficient energy to go from P to Q. They might get energy because of this potential difference, and these electrons can move from P to Q, so the current will increase. Do we understand this?
Yes, sir.
So the current will increase if I increase the potential of point Q and make Q more positive with respect to P. Will this thing keep on going forever? Will the current keep on increasing till infinity? If I keep on increasing the voltage, will the current always keep on increasing, or will something happen? Will the current keep on increasing always, or will something happen? If I keep on increasing this value of Q with respect to P, there will be a point when the current in the circuit becomes maximum, because all the electrons which are at point P, which has been liberated, they are now able to reach point Q. In this case, the current in the circuit becomes constant, and this current is known as the saturation current. Do we understand what I have said?
Yes, sir.
So, when the potential of P and Q are same, a very small current flows. This is of practical no value. When the potential of point Q is made positive, current starts to increase, but it cannot increase till infinity. There is a point when this current becomes constant. That value of current is known as saturation current. So far, so good. Have you understood till this point?
Yes, sir.
I'll give you 2 minutes to note this down. So what we have seen is, if we keep on increasing the potential of Q, which is anode, positive, if we make it more and more positive, current will keep on increasing. It will reach a maximum value. That maximum value is known as saturation current. Do we understand saturation current? Yes or no?
Yes, sir.
It is the maximum value of photoelectric current that can be produced in a discharge tube. Do we understand this?
Yes, sir.
Now, if you want to increase the current any further, you will have to increase the intensity of incident light. Now, we will discuss this term of intensity of incident light just after this one. Here, you just note down that if you want to increase the current any further, you will have to increase the intensity of the light. Photoelectric current depends on, number one, potential difference between the electrons till saturation. It depends on the intensity of light I, and it depends on the nature of the photoelectric surface. Here we have a graph between intensity I, sorry, between intensity I, which is plotted here, and the photoelectric current I. As you can see, this photoelectric current is directly proportional to the intensity, subjected to the condition that the frequency must be greater than F naught. If frequency is less than F naught, nothing will happen. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Now, there is always a confusion between this energy of the photons which is falling and the intensity of the photons which is falling. Now, you might recollect that when we talked about intensity of radiation, we talked about energy falling per unit area per unit time. So, that would mean that intensity of radiation depends on the energy of radiation. Yes, it depends, but let us try to understand this thing in the context of photoelectric current. Now, whenever we are talking about the energy of radiation, we just move this. When we talk about the energy of the photons, when we talk about the energy of photons or energy of the radiations in this particular context of photoelectric current, whenever we are talking about the energy of photons, this energy of the photons E will be equal to H into F. Energy of the photons or energy of the radiation is E, and that E will be equal to H into F. I hope you know this. It depends on the frequency. Oops. This energy of the photon E will be equal to H into F. That means this energy depends on the frequency of photons. Do we understand this? This energy of the photons or energy of the radiation will depends on the frequency of the photons. We understand this?
Yes, sir.
In fact, this E is directly proportional to F. That means if the frequency is increased, energy of the photon increases. Yes or no?
Yes.
For photoelectric effect, PEE we call it, the frequency of the radiation must be greater than must be greater than F naught, or the energy of the radiation must be greater than the work function. Do we understand this?
Yes, sir.
Now, by Einstein's equation, we have seen that this E will be equal to W naught plus the maximum kinetic energy. Yes or no?
Yes.
That means you can write this HF will be equal to HF naught plus KE max. That means the maximum kinetic energy directly proportional to F. Yes or no?
Yes, sir.
So, if frequency of the photon is increased, that means the maximum kinetic energy of the electrons will increase, or the velocity of the electrons will increase. Yes or no?
Yes.
It has no effect. It has no effect on current. Yes or no?
Yes, sir.
It has no effect on current. It will only change the maximum kinetic energy of the electrons which is falling, and this F must always be greater than F naught. Do we understand this?
Yes, sir.
So energy of the photons, whenever, first listen to me, I'll give you time to write. The energy of the photon, whenever this term energy of the photon or frequency of the photon comes, remember it has only one and one effect, and that effect is on the kinetic energy of the electrons or the velocity of the electrons which are coming out. Do we understand this?
Yes, sir.
Now the second thing that is going to come, and therefore I'm going to write it side by side, is the intensity of photons. And here is where the confusion might start. As I told you before, intensity of radiations is energy falling per unit area per unit time. But when the energy is falling per unit area per unit time, it not only depends on the frequency, it basically depends on the number of photons which are falling. Yes or no?
Yes, sir.
So this intensity, whenever we talk about the intensity in this particular chapter, this intensity I is proportional to the number of photons. Number of photons which are falling. Do we understand this?
Yes, sir.
If intensity is increased, the number of photons, let me call it as small n, the number of photons will increase. Yes or no?
Yes, sir.
If the number of photons increase, then number of electrons which are emitted will increase. Yes or no?
Yes, sir.
Or it will increase the photoelectric current, but that is only possible when the frequency is greater than F naught. Do we understand what I'm saying?
Yes, sir.
Therefore, we can note that the intensity of photons only affect the electric current, the photoelectric current I, and not the kinetic energy or the velocity of electrons which are emitted. Do we understand this?
Yes, sir.
Is everyone clear between the difference of intensity of photons and the energy of photons? The energy of the photons, I repeat, depends on the frequency of the photons, which in fact is going to control the maximum kinetic energy or the velocity of the electrons which are emitted. On the other hand, when we talk about the intensity of photons, we are talking about the number of photons which are falling. If the number of photons increase, if more photons are falling, they will collide. We are taking them as particles. They will collide with more electrons. When they collide with more electrons can be emitted, but that will only happen when the frequency is more than the threshold frequency. If you have more electrons which are emitted, we'll have more photoelectric current, but the speed of the electrons does not depend on the number of photons, it depends on the energy of the photon. Do we understand this?
Yes, sir.
Everyone understands this? Can I have raised hand that we have understood this? I'll give you 2 minutes to note this down. Now we have seen what happens if Q is made positive with respect to P. Current increases, it reaches a maximum value. That maximum value is known as saturation current. If you want to increase the current further, you have to increase the intensity of the radiation. You have to make more electrons, more photons fall. Do we understand up till here?
Yes, sir.
Now let us now understand what happens if you do the reverse. What do you mean by doing the reverse? If now the plate Q is maintained at a negative potential with respect to P, and you make it more and more negative, then what will happen? Fewer and fewer electrons will reach the cathode and the photoelectric current will decrease, yes or no?
Yes, sir.
At some point, the photoelectric current will become zero. That point or that voltage is known as stopping potential. Stopping potential means you have stopped all the photoelectric current. That means you have stopped the electron which had the maximum kinetic energy. Do we understand this?
Yes.
That potential is known as stopping potential, denoted by the legendary letter V naught. If the potential of Q is negative but less than the stopping potential, you can call it retarding potential. You are decreasing the speed of the electrons. Do we understand this?
Yes, sir.
What is the relation between stopping potential and kinetic energy? Remember, stopping potential comes when you are able to stop the fastest electron. Therefore, the kinetic energy of the fastest electron will be equal to E into V naught. Do we understand this relation?
Yes.
I'll give you 2 minutes to note this down. One more thing you have to note, evident, the stopping potential depends only on the frequency or the wavelength of the incident radiation, because kinetic energy depends on the energy of the radiation, or it depends on the frequency of radiation, or it depends inversely proportional to lambda. Do we understand this? Stopping
Yes.
potential depends on the energy of radiation and it does not depend on the intensity of light. Remember this. I'll give you 2 minutes. Read each and every point very carefully. Most of the questions that are going to come will be in the form of theoretical questions. Please be careful. Take your time. We have enough time. Okay, then we move ahead and we draw the graphs and everything based on this chapter is based on these graphs. We have already seen some of them. We will still keep on seeing more of them. There might be a repetition, but the more you repeat, the better you become. Sant Kabir Das has said, karat karat abhyas ke jadmati ho sujan. So if you keep on practicing the same thing, you are bound to become good. You are bound to become good in the same thing. So the first graph that we are going to see, a part of which we have already seen, is a variation of photoelectric current with potential difference. How will the photoelectric current depend on potential difference? Yes, my dear friends. How will photoelectric current depend on potential difference? Do you understand the meaning of potential difference? Which potential difference are we talking about? Huh?
Positive potential.
What positive potential? Potential difference between the anode and the cathode. Do we understand this?
Yes, sir.
And the graph of photoelectric current with potential difference looks like this. Do we understand?
Yes, sir.
Here, it's not shown, the graph becomes straight like this. What is this current known as? IS. Do you understand the meaning of IS?
Yes, sir.
What is IS? Huh?
Saturation current.
And what is the gentleman?
Stopping potential.
What are the main points of this observation? I will give it to them. It would be a repetition probably, but the more we repeat, the better we become. At zero potential, a small current will exist because there will be some electrons which will be able to go to the other side. Do we understand this?
Yes, sir.
If we keep on increasing the anode potential, what happens, my dear friends? More current will flow. Do we see this?
Yes, sir.
At a certain value, what happens?
It becomes constant.
It becomes constant because more electrons cannot be emitted, and most of the electrons that were emitted, all of the electrons that were emitted have now reached their destination. What is their destination?
Anode.
Their destination is anode. Do we understand this?
Yes, sir.
Now comes the scenario where we are going to make the anode negative with respect to the cathode. Do we understand this?
Yes, sir.
And then what will happen? You will see that at a certain potential, which is known as the stopping potential, the current will cease. E kinetic energy max will be equal to E into V naught. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Your time starts now. Try to draw the diagram on your own. Try to write the observation on your own. If you can do that, that means you have understood what has been told to you. Now, as you can see, for a given frequency, your saturation current is fixed. Now, for a given frequency, if I want to increase the saturation current, how can I increase the saturation current for a given frequency? Now, this is the graph between saturation current and potential difference drawn for the same frequency but at two different intensities. Intensity I1 and intensity I2. Where is my ding? Okay, it's there. They are drawn at two different intensities, I1 and I2. As you can see here, the frequency F is fixed, and therefore you can see the stopping potential being same because stopping potential depends on the kinetic energy of the electrons, and kinetic energy of the electrons depends on the frequency. I2 and I1, two intensities are given. Which intensity will be more and which intensity will be less?
IS2 is more, IS1 is less.
IS2 is the saturation current at frequency 2. IS1 is the saturation current at frequency 1. Which frequency is more? I1 is more or I2 is more?
I2 is more, sir.
I2 is more. As you can see, if you want to increase the saturation current, you have to make more photons to fall. More photons falling will emit more electrons. More photons falling means number of photons have to be increased. Number of photons have to be increased. That means you have to increase the intensity of the electrons. Do we understand this?
Yes.
You have 2 minutes to note this. So you can see this. Same diagram, you can just write these two things. The saturation currents increase with increase in intensity, and stopping potential does not depend on intensity. Do we see this?
Yes.
These are the next sets of graphs. In the first set of graph, what do you see? There's maximum kinetic energy. You just have to note the important point. Maximum kinetic energy is E into V naught. Now remember, this maximum kinetic energy is not the kinetic energy of all the electrons. The kinetic energy of all the electrons vary from 0 to Ke max. Do we understand this?
Yes.
So for any electron, the kinetic energy will lie between 0 to the maximum value, and the maximum value is E into V naught. And how does this vary? This is how it varies. This is how it varies. Do we understand this? So electrons will have all types of kinetic energy starting from 0 to maximum. Do we understand this?
Yes, sir.
Now, if you use different color lights, that means different frequency lights, you can see the stopping potential keeps on changing. Do we understand this?
Yes, sir.
Which stopping potential will be more? This is F3, this is F2, and this is F1. What will be the sequence? Which frequency will be more? Which frequency will be less?
F1, sir.
This is the graph for frequency F3. This is the graph for frequency F2. And this is the graph for frequency F1. Which frequency will be more? Which frequency will be less?
F1.
What F1? More or less?
It is less, sir.
Which is the maximum frequency?
F3 will be max.
So you can see that the stopping potential is directly proportional to the frequency F. Do we understand this? Negative value, I mean. Remember here, more negative does not mean less. More negative means more. Do we understand?
Yes.
I'll give you 2 minutes to note this down. Well, then we have seen the graph of photoelectric current with voltage. We have seen also what happens when you increase the intensity at the same frequency. We have also seen what happens when you change the frequency. The stopping potential depends on the frequency. Are these points clear to everyone in the class?
Yes.
Well, there are few more variations of the graph left. We don't have time for do them today. Remember, any one of these graphs is going to come into the exam. So we will continue this class in the session for tomorrow, and hopefully we will be able to wind off this photoelectric effect in tomorrow's class. There are only two things that you have to remember here. One is the Einstein equation. We are all going to revisit it and write it in all the forms that it is possible. And the other thing is the theoretical aspect of this. You must understand what intensity, how intensity affects all the components, how the frequency changes, and what happens to the kinetic energy. If you can remember this, you are assured that if this question comes, you will be able to solve it. So we'll continue this in the next class. Take care and have a nice day. I hope you have understood everything that we have discussed in the today's class. Yes or no?
Yes.
Well, if you have any doubts, please ask me after the class. Take care. God bless you.
Thank you, sir.